parameter, C, right? It's called C, where it's contacts per unit time, right? Given individuals a certain number of contacts per unit time. And in an agent-based model, we may have individuals in that agent-based model who are embedded in networks. And if we have them, so if we have those individuals, okay, I got to switch microphones here for Bernice's sake. So if we have them in the agent-based model embedded within networks, those networks are have a certain number of connections of that agent, right? A number of connections of that agent to other agents, right? Does that make sense? So they're in a network, and that network affords them a certain number of connections to other agents. Now, that's a separate issue, largely orthogonal to the issue of how many contacts they are having across those connections, right? You can imagine a situation where an individual has 100 different connections to different individuals, but they only have one contact per unit time with any one of those individuals, right? In that situation, so they have a great diversity of contacts in terms of number of different individuals, but a very low rate of contacts. Alternatively, you can imagine a situation where they have a very high rate of contacts, and those contacts are all with a single individual. And so when it comes to an agent-based model, we have an issue of how many network connections does a particular node have, a particular, say, person, and then how frequently are they engaged in an actual contact across those connections. And what I was trying to do in assignment 3 was to set up the situation such that you had a similar rate of contact between these two models, even though the number of connections within the agent-based model may be different than that rate. Because the number of connections has to do with the diversity of people with whom you're interacting. Diversity in a loose sense. In other words, how many different sort of people. The quantity of different individuals. And it's distinguishing those cases where you're having many, many contacts but with very few people versus many, many contacts with large numbers of people. And that's useful. And so I was trying to normalize across the two models the rate of contacts, even though the number of different connections of that index individual would be different, in a network might be assumed to be, say, quite small compared to what would be conceptually implied in a system dynamics model. So I don't know if that's answering William's question or partially addresses it. Can you? Does it partly speak to it? Yeah. Oh. Okay. So there was further an issue in assignment 3 where when I was comparing the results of network models that are all agent-based with each other, I tried to normalize for the number of distinct connections of an individual as well. So I tried to have it so that if you had a random network, you are connected on average with the same number of people that you were connected with in a scale-free network, or on average the same number as in a small world network, or what have you, among the different different network models. But I did want to bring out this difference between an agent-based model and a system dynamics model. And I'll let you muse on that for a little bit. Let me ask this, just to sort of probe it, to probe the issue. In a system dynamics model, what sort of assumption is there about how many distinct individuals with which you're in contact? Is that specified explicitly? No, it's not specified explicitly. What do you think is the assumption? Do you think the assumption there is that you're doing all your mixing?
Yeah, there's a homogeneous mixing and everybody's in contact with everybody.
So you're in contact with large numbers of different individuals. You're like in a bath of a heat bath from a, okay, that's a, sorry. The physicists will relate to that statement. Probably no one else here will. You're in just this like sea of individuals. The Chinese have a name, an idiom for this. Ren San Ren Hai, meaning like mountain of people, sea of people. You're just surrounded by people. Chinese can relate to this from being there, and that brings you into contact with lots of different people. That's what's going on in a system dynamics model. There's this homogeneous mixing. And by contrast, you can represent that in an agent-based model, but you can also capture those cases where you're in contact with just one individual, say, on a repeat basis. Frequently on a repeat basis with one individual. Let me ask this, ladies and gentlemen. Could that make big time? I mean, if you're just with one individual, you could be sneezing up, well, okay, this sounds weird. You could have many contact events like sneezing, but it's only going to infect how many people at most? Yeah, if you're situated in a situation where you're only contacting one person throughout the course of your illness, what's your R naught going to be? At most 1, right? Your basic reproductive number. Even if you're extremely contagious, you're going to only be jeopardizing one person. Whereas with random mixing, it's like you're in the middle of a bus station. You're going to be contacting all these different individuals, and you could spread it to large numbers of different people, right? Very large numbers of different people. Think about it with a transmission risk of beta of equal to 1. Can anyone give me the common formula for basic reproductive number for a system dynamics model? What is a basic reproductive number?
The multiplication of all the force of action.
Good. Yeah, so, and duration, so it's going to be, so this is going to be the number of people, a given index infective infects, that is an individual in a totally susceptible population. They're surrounded by a sea of susceptible people. How many people are they going to infect over the entire course of their illness? In other words, before they recover. Well, it's going to be, can anyone give me a formula for it? In terms of the basic quantities, we talked about beta, C, and suppose there's a duration of illness, D. Give me a formula that's dimensionally consistent. So R naught here is going to be some number of people. So, okay, C times beta. Let's sort of reason through this. So they have C contacts per unit time with all these other people who are susceptible by definition. They're surrounded by a sea of susceptibles. So we're dealing with one infected flying in to a city. No one else is infected or recovered or protected. They're all susceptible. So C people per unit time they encounter. Of those, they transmit to C times beta. And then, what's the key other component? What is this dimensionally? C times, what is this dimensionally? Suppose C we measure in, we'll actually say it's in people per unit time, but let's talk about it as per unit time, because it's actually person per unit time. In other words, person per. So it's 1 times time times what's the units of beta? It's actually a probability, a likely. So it's units are 1. It's unit. In other words, it's because no matter how we measure it, it's just a fraction of them. Again, it's like what fraction of this area is occupied by this console here, of this stage area. It doesn't matter whether I measure the area in square meters or square feet or in hectares or acres. I can measure in all those things. And the same fraction is going to turn up the fraction occupied by this console. Right? It's like, man, if I had a coin here, flip a coin, it doesn't matter whether I'm measuring coins as single flips or tens of flips or thousands of flips, the same fraction of coins would yield heads. That's why a fraction is dimensionless. Okay, so dimensional units. We still got a 1 over time. What do we need to make this a complete count? We need duration. Thank you. We need a time. We need a time to give us a full count of individuals. Okay, so it's C times beta times D. So if you add this individual who is perfectly infective, like typhoid Mary on steroids or something, that's a weird notion, but they were incredibly infective. And they were circulating, let's say, and how many people would they infect over the course of their illness? If they were perfectly infective, they'd infect
1 person per contact.
Okay, and C times D total people. And that'd be quite different if typhoid Mary, were only in contact with 1 person over the course of the illness. If she had only cooked for a single individual, and was the special order cook for some reclusive millionaire or something, she could only infect 1 person over the course of her illness. So this is quite different. She's infecting lots and lots of people here, C times D. Okay, now, however, our remote audience, I need to switch to a new microphone here. So I'm going to just stop for a minute, and I'm actually going to stop this recording.